الرحمن الرحيم. الحضور الكرام، يسرني أن أرحب بكم في الدورة الجديدة لملتقى كتاراتك، البوابة الأولى لعالم التكنولوجيا المتطور، والذي يهدف إلى نشر الثقافة الرقمية على نطاق واسع، والعمل على جعلها متاحة لجميع الزوار باعتبارها عاملاً أساسياً لتنمية القدرات الإبداعية والمعرفية. في وقتنا الحاضر أصبح الذكاء الاصطناعي موجود حولنا في كل مكان، ونتعامل معه في حياتنا اليومية، ولذلك يلقى اهتماما متصاعدا. وبفضل الكاميرات وأجهزة الاستشعار المدعومة بالذكاء الاصطناعي، أصبح من الممكن اليوم التحكم في حركة المرور، وكذلك التنبؤ بالحوادث وتفاديها. إيمانا بأهمية الذكاء الاصطناعي، يسرنا أن نقدم لكم الدكتور يان يانغ من جامعة حمد بن خليفة ليعرض لنا محاضرته حول استخدام الذكاء الاصطناعي لمنع الحوادث المرورية في المدن الذكية. تفضل دكتور.
Good morning, everyone. So today I'm doing this webinar about preventing traffic accidents with artificial intelligence technologies. So about myself, I'm an associate professor at the College of Science and Engineering at Hamad bin Khalifa University. I'm also the coordinator of AI research in the college and one of the founding members of the division of the ICT, Information and Computing Technologies. In the past, I also worked as a professional consultant for a local technology company. So before we talk about our main topic, let's briefly review events in the history of AI. So this picture I found in Google from a company. So they summarize the major events in the history, in the timeline of AI. So as you see, in the beginning, most people focus on theoretical work because at that time, we didn't have the strong computers, we didn't have the big data, and we didn't have the efficient algorithms. And as a result, most of these works are about the theory of how things could work, but they didn't build a real system. So starting from 1965, people have been working on natural language processing technologies. So here you can see that as early as 1965, people started building chatbots. And then later on, those technologies evolved into common technologies like Siri, Google Assistant, Cortana, and so on. So now it's fair to say that the computer can kind of understand what humans are saying, and the computers can even make a short conversation with a human being. And also you see that a major indicator is how well you can play a game. So as a result, many researchers using AI to play games. So in this major event, IBM Deep Blue defeated the human chess champion in 1997. In 2011, another IBM AI system, the best human players of Jeopardy. So in 2016, Google's AlphaGo system defeated this the human champion of the Asian Chinese board game of Go, which at that time was considered far beyond the state of the art. So in those years, around 2015, 2006, people widely anticipated that this will happen after 10 years, maybe 2030 or something, but it happened much earlier in 2016. And after that, the computer can pretty much beat humans in every game. But if you look at those things, theory, chats, playing games, and here university courses, while they are remarkable from the technology point of view, from the application point of view, they don't look that important, right? So yes, you can chat with a computer, so what, you can play a game with a computer, but what's so significant about that? So this is another image I found online from a major university. So they summarize a few breakthroughs that they think are the most important. So here we have the computer recognizing objects. So this ResNet, which was indeed a breakthrough in convolutional neural networks, reached 96% accuracy I guess that's for the ImageNet computation without. So they also have many layers. So from the technical point of view, this is and it was really revolutionary. But from the application point of view, yes, you can recognize some objects. So what, right? So as humans can also recognize the same objects without much difficulty, or sometimes with a little bit of training. So here, the computer can transcribe speech. Okay, so this is not even understanding speech. So you say something, and the computer can output some text. So the text is what you said, but you can argue the computer doesn't really understand what you're saying. So this has been applied. If you watch YouTube videos, you can see there are automatically generated captions. So in this breakthrough, the computer can answer some questions related to an input piece of text. So this look remarkable is like the computer is really thinking about things because now the computer is given some information and you ask a question and the computer answers, give you the answer. But if you look into the specific setting of this computation, so yes, the computer is provided a piece of text, usually a long paragraph, and yes, the computer is presented some questions, but in this computation, the answers to those questions are usually fragments of the input text. In other words, the computer isn't thinking, the computer doesn't intelligently answer the question, but instead it's more like a search operation. The computer goes to the input text and identify the fragments of the text that's most relevant to your input question. And sometimes you can also do some post-processing to make the answer that reads better or more fluent. But the idea is are all embedded in the input text. So in this breakthrough, the computer is able to translate from one language to another. So you can argue that the computer must gain a certain level of understanding in order to do the translation. But on the other hand, the computer isn't able to do anything else except for outputting the same text in another language. So a common thing among those so-called AI breakthroughs is that they aim for this concept of human parity. So in their mind, the ultimate goal of AI is to reach the intelligence level of humans. So if you think about it, this is not wrong because yes, humans do have a very high level of intelligence. But from the application, is this the only thing you want to do? Well, if you just want to reach human parity, why don't you just hire more workers, right? So maybe we hire more workers from some foreign countries, and then those workers, and then we can hire even experts, and they will solve the problem. So why do we need AI to do this? And keep in mind that AI systems are not cheap, and their accuracy, although we aim for human parity, they haven't reached that level yet. So maybe in the far future, we'll have AI systems replacing human workers. But as of now, AI system cannot replace humans, and we need to find more meaningful applications for AI. So now let's look at this diagram a bit more. And we do see a few other things besides playing games, chat with people, theoretical work, and university courses. So here you see this, I believe, is a very important application. So if every car can drive itself, then we not only save manpower, now we don't need the human drivers anymore, so we don't need the taxi drivers, so maybe much fewer parking lots. But we also reduce the risk of driving. So that, I believe, is more important than cutting the cost, because AI system nowadays isn't really cheap. So what if instead of reducing the cost of driving, we also save a few lives? And this one is about robotic home cleaner. So you may argue that this robotic home cleaner is very remarkable. So all it does is to sweep your floor. But here it shows a promise that you can put an entire AI system into that tiny machine, and this machine can somehow intelligently sweep your floor. And maybe tomorrow we can also put a much bigger AI system into a small machine, and then machine can do more useful works. And also in this breakthrough in the 1980s, people have been working on expert systems. So although we have abundance of manpower, we don't have that many experts here. So one example is medical expert. So when you will get a disease, you want to go to a hospital or clinic to see an expert doctor. So you don't want a random person to diagnose your disease and give you medicine. So hopefully in the future, AI can learn the expertise from the human being and not just random human, not just the intelligence level of a random human being, but the intelligence and expertise and knowledge of the real expert. So today we focus on a particular practical AI, which is to prevent traffic accidents. So hopefully in the future, all the cars drive themselves and we don't have traffic accidents anymore. But as of today, self-driving cars are still a distant goal, and we still have human drivers. So so now let's see with the current technology level of artificial intelligence, what we can do to prevent or reduce traffic accidents. So in today's seminar, we'll talk in 45 minutes about two major topics. So the first topic is recognition, which means understanding what's going on. So in a vehicle, if you understand what's going on around you, then the AI system can give warnings to the driver when some danger is going to happen. So another important topic is prediction. So in this scenario, the danger has not really, but you make a prediction that some danger is going to happen, or they are likely to happen, and therefore you can take some preventive measures. So the specific application I mentioned in this talk is to help the traffic send patrol cars to regions and zones at a specific time in order to prevent traffic accidents. So first, let's talk about recognition, in particular, understanding what's going on from the data presented to us. So one of the most important data source is the camera. There are different types of cameras. Of course, everybody has nowadays has a phone. The phone has a camera. So with the camera, you can record a video and you can shoot a nice photo. So today we focus on two types of cameras. One is the camera within the vehicle. Okay, so for example, this car, you can imagine that it's equipped with several cameras. So you have a front-facing camera at the dashboard. You also have back-facing camera. So for example, most cars now have a system for reversing. And also some vehicles are also equipped with LiDAR systems. So they also like cameras in the broader sense, but they have 3D inputs, and they have 360-degree surroundings, so that detect everything around the car. Okay, so nowadays it's not that hard to recognize things from a picture. For example, from this photo, we can see that there are 3 traffic lights. Okay, there are a few poles, and this is the vehicle in front of you, and you have some road signs. So this says turn right. Okay, so this says go straight. So if you are in this lane, and then suddenly you are trying to turn right, that action. First of all, you see that this is a solid line, so you are not supposed to turn right at this point. And second, there is a vehicle in front of you. So if you suddenly turn right, you might hit this vehicle. Okay, so from this photo alone, a lot of information. But now we are explaining from a human point of view. So for a human, it's easy to understand those things. So can artificial intelligence understand those things? Well, it can, but there are a few restrictions. So first of all, AI can recognize those objects, but the accuracy is usually not 100%. So you can say this is a pole, but the computer may say this is not a pole. Okay, maybe this is part of the background. So maybe this is just a drawing or something. The computer may not recognize a pole as you expect. And second, and more importantly, the computer may not recognize things fast enough. So nowadays, when we run AI systems, we usually run them in the data center. So in the data center, we have those very strong computers equipped with many GPUs, so that you can get high accuracy with this. Even with those systems, sometimes you have to run for several seconds to get a picture. But now you are in a vehicle, okay? So how do you pass the scene quickly and accurately? So you have like 0.01 seconds to pass the scene, so that you can warn the human driver or you take precautious action. Another thing is that now you are in the vehicle and you don't have a strong computer, okay? So you can't really carry a large workstation desktop in your car. You don't really have that much power. Even you have only 120 watts in the cigarette lighter. So you could argue that how about let's transmit this picture through 5G to the data center, and the data center will send back the results. Well, you could do that, but what if your 5G connection is interrupted for a few seconds? So this won't work. Another application of this camera thing is that we can also recognize objects and parse scenes from a surveillance camera. So this has several applications in practice. So first of all, the surveillance camera can know what's going on, so that it can inform the police. Okay, so maybe the surveillance camera has detected an accident, so that it can tell the police that the accident just occurred. So police sent the patrol vehicles there. Another thing which I found more interesting is that what if the surveillance camera can send a warning sign to the driver? So let's say you can detect danger scenes very quickly. So for example, maybe the car does not see a danger in front of him. Maybe his vision is blocked, but the surveillance camera can see this, and the surveillance camera sees that you are accelerating very fast, and there's an object in front of you that you don't see. So maybe the surveillance camera can also give you a warning. So as you see here, from the surveillance camera's point of view, the objects look very different. For example, the vehicle looks like this. Okay, so and also a bit different from the car camera is that in the car camera, you don't see a very crowded scene. So here you see a vehicle, and you see some poles and some objects, a traffic light, and that's it. But from a surveillance camera high above, you often see a very crowded scene. Okay, so there are many vehicles and many drivers, motorcycles, and maybe also pedestrians. So many things. So how do you separate each of them, and how do you track them across different frames of the video? So those all become challenges. And furthermore, how do you do the same things in a low light condition? So for example, here is a scene in the Oxygen Park of our university. So here, for example, the whole scene in general is pretty dark, but you do have those very bright lights, so they produce flares. And then now you have this person walking here, but even as humans, we hardly see that this is a person unless he start working. So from the video, we can understand that he's walking. This is a person walking from the movement, but from a static image, it's pretty challenging to recognize those people and to know that they are pedestrians, not background. Okay, so now let's summarize the key challenges. So first of all, we want embedded AI systems, and I forgot to mention also at a reasonable cost. So nowadays, a very good computer at the data center can cost you more than the car. So you don't want the computer in your car to cost more than the car. So you have to produce a system at a lower cost than what than they currently cost, and also you want them to be embedded to your vehicle or to the pole. So so that means they have to consume relatively low amount of energy. So in the vehicle, you have those 120 watts. So on the pole, usually you have those solar panels. So if you around maybe 60 or to 100 watts. So within this energy budget, you must do what you are supposed to do, and you have to do your job really well. Challenge is real-time recognition. So your AI model must be very fast. And if it takes a few seconds to recognize a danger, then that's probably too late. And finally, you need high accuracy, especially in the low light challenging conditions like this. Okay. At our university, we have been carrying out some research activities related to those challenges. So first of all, we are testing the novel embedded computer systems. So what we can buy right now are mainly NVIDIA Jetson devices. So NVIDIA Jetson currently sells these NX Jetson devices, which are not so expensive. They are like maybe $150 to $200 each. And what we did in our lab is that we are trying to build a cluster of those. And so, so this picture shows you the relative size of our system. So you see that the main board for the entire cluster, and this is the small box. So you can imagine this box is as big as your typical iPad mini. So in the size of iPad mini, you are going to put 4 NVIDIA NX GPUs. And then those GPUs will communicate through a network. And what we are trying to do is to get as much computing power as possible out of this configuration. So NVIDIA also sells professional systems. So unfortunately, we haven't been able to get a hold of such a system. So those systems are usually 1 or 2 generations ahead of those research prototypes. So this one we have, this is in the Volta generation, which is around 2 generations behind the current commercial system. But due to a limited budget, we are playing with those systems. And it's possible that our system is so efficient that we can even outperform the larger system by NVIDIA's commercial system. Okay, another thing we have been doing is to compress the AI models and also to accelerate the AI models. So to achieve our goal, we do research not only on hardware, but also on the software side. In particular, before the AI models, they might take several gigabytes. So now, after our compression techniques, we can compress them to maybe less than 10 megabytes. And as a result, the speed of the AI system is also much improved. And therefore, we can achieve real-time performance. Besides that, we are also doing research on novel computer vision models. So nowadays, the most popular computer vision model is the vision transformer, which has been shown to outperform the traditional convolutional neural network models. But the problem with those vision transformers is that they are usually very large and they are very slow, which motivate us to compress the models further and to accelerate them through software and hardware. Okay. So before we go to the second topic, I'd like to show you a video about a real scene that we observe in the surveillance camera. So this is a video of our oxygen park. And this video I also showed you the prediction results of a popular network. So this is actually ResNet 50. So you can see that the AI has many problems. So first of all, it recognizes this pole, this light pole as a person. So here we say objects, but internally we only detect one class, which is person. So you see that the AI mistakenly took this pole as a person. Second, you can see that here sometimes it detects this as a person. And also when a real person passes by, sometimes it doesn't detect that person. Okay, so let me scroll to a scene where we have some people here. So for example, in this scene, we have this person who's walking, but the computer doesn't detect this person. So you can imagine that if we use this in the traffic application, and those are pedestrians, so missing a pedestrian can lead to rather catastrophic events. And also you see that the detection result is rather inconsistent. So for example, here, sometimes it does detect this person and sometimes it doesn't. So the reason is that this model, which is the popular open source model, doesn't consider the video aspect of our input. So it performs detection frame by frame, and therefore it doesn't carry the knowledge of the previous frame to the current frame. So you can see that the detection results is on and off. Furthermore, you see that this is a challenging condition in terms of lighting. So you have those flares, and in general, this scene is dark. And therefore, we don't get very good results through this open source model. So at HBK, we are developing novel models that overcome these problems. Okay, so now let's come back to our presentation. So the second part I want to present is we want to make accurate predictions of problems before they occur. So one specific project that we have been doing is to predict the zones and time periods that traffic accidents are likely to happen in the coming 24 hours. So why do we want to do that? Because if we know that some traffic accidents are likely to happen, then we can send police patrol vehicles to those places to prevent them. So I don't know if you have watched this movie about pre-crime. So in that movie, they sent some criminal police officers to a crime scene that's going to happen. So here we are sending traffic police officers to a place where accidents are about to happen. Okay, so now let me show you a demo of our current system. So this demo system can run on several different type of machines. And of course, you can run this on a big screen. And you can also run it on an iPad or phone so that you can discuss about those where to send the traffic police while taking a mobile device. So this is the map of Doha. In the first step, the user first which day and which shift that you want to make the prediction. So we assume that the traffic police divide the shift into 4 shifts per day. So we learned this information from our collaborators in MOI. So after selecting the date and shift, so in reality this will be today, but for the demo purpose, I'm showing you an arbitrary date. So after that, the computer AI system will make a prediction for each of the zones in Qatar. So there are in total about 90 something zones. So if I remember correctly, maybe 98 or 99, I don't have the precise number. So many of those zones don't really have traffic accidents. For example, this zone, although it's very large, it doesn't have a lot of traffic, and therefore predicts that it doesn't have any accidents in the coming 6 hours. But for some zones, although they are very small, for example, those zones in the city center, they are more likely to suffer from traffic accident problems. So now the AI makes those predictions, And for each zone, if you click into that, you can predict, for example, in the next 6 hours, we might have 8 accidents. Okay, so the numbers here, they are not real. So because we have a confidential agreement with MOI not to release the real data. So the numbers here, they are synthetic, but they show you the idea. So the AI system predicts that there might be 8 accidents happening in this zone. So if there are so many accidents that's going to happen, then you can send traffic police to that zone, follow the zone. Okay, so this is another date, and you can also choose a historical date to view what really happens on that day. So in that case, it won't be a prediction, but something that already happens. So you can compare what's going to happen from the AI's prediction to what's historically actually happened in that day. Okay, so also here, synthetic dots will show you what accidents happened there. Keep in mind that those dots are just synthetic; they are not real accidents in the past. Okay, so this is another visualization of traffic accidents. This is a heat map of accidents. So you can see that over a long period, this is for the entire year, traffic accidents tend to happen everywhere, especially in the city areas. From this traffic accident data, we extract the density from those accidents. So for example, you can see that here in this junction, there are many accidents happening. And from this information, we can tell the police something is going on here. So maybe we should investigate. Maybe there's a design problem for that. And maybe we should send more traffic police to that junction during a specific time. So this is more for review of the traffic conditions and to help the traffic police make better decisions. Okay, so these are more examples of those traffic density information. And here you can click into a specific accident and see what's going on here. So it tells you the nature of this accident and whether there are serious injuries or even death. Okay. So you can also zoom out the entire city and quickly get an idea about where traffic accidents are distributed. So from this, the police officer can make an informed decision about where to send the traffic police. So this work has been ongoing with collaboration with Ministry of Interior, the GDIS department. So there are a few key technological challenges in this work. So first is, how do we make accurate predictions? So if we make misleading predictions, so for example, we say there will be a lot of accidents, but it turns out there are almost no accidents there, then we waste manpower from the traffic department. Or if we say there's no accident in this zone, but actually quite a few accidents happened, then we waste an opportunity to the number of traffic accidents. So in order to make accurate predictions, we've used a specific technology called graph neural networks. So compared to other technologies, graph neural network is able to utilize multiple sources of information, which include historical data as time series, the current observations, and also data from surrounding zones, and also to zones that are not directly connected to this zone that we're trying to make a prediction, but there's a historical link between those zones. For example, if you have a highway connecting to distant zones, so the number of traffic accidents for those zones might be connected, although they are far apart. So our current accuracy is about 89%, and this improved over the previous model's accuracy, which was about 81 or 82%. And we are still trying to improve the accuracy of our prediction model even further. So another technological challenge here is that once we deploy this system in practice, so police will send their patrol vehicles to those places. So police intervention will also affect the pattern of traffic accidents. So it's possible that because you send those patrol vehicles, the number of accidents will decrease. But what if you send those patrol vehicles, maybe people choose a different route, and as a result, other zones have increased level of traffic accident. So we don't have data in this aspect, and we plan to investigate this issue in the future after our system is deployed in practice. Okay, so in summary, today we talk about application of AI. In the history of AI, most people focus on reaching human level intelligence. But I argue that human level intelligence, although this is technically challenging, it is useful in some applications. It is not everything that AI does. So here I want to shift our focus from those lab experiments to real applications that can make a difference to our lives. So now we finish this webinar, and I open to take questions. Thank you.
نشكر الدكتور يان يانغ ونثمن مشاركته معنا ونتمنى له دوام التوفيق والنجاح. في الختام نود أن نشكركم على حضوركم وتفاعلكم معنا. يشرفنا أن نلتقي بكم في سلسلة ملتقيات كتارتك القادمة.